All right, welcome everybody. So our speaker today is Professor Rumpf from the University of Bonn, and he will talk about Riemannian calculus in shape spaces. Thanks for coming, and please go ahead.
Well, thanks a lot for the invitation. It's a pleasure to be here online at least. I would like to develop with you a geometry of different shape spaces, but just let's get started. Oops. So this is joint work with many people over the last 10 years. So this started with Leah Barr and so where is he? Benedict Wirth and Guillermo Sapiro, where we did first experiment with geodesics. So then Alexander Eflan, Benjamin Berkels, Bernd Heeren, and recently Marko Rajkovic and Joza Sassen from my group worked with me on this topic, and we cooperated with Tom Fletcher, Klaus Hildebrandt, Erich Kobler, Thomas Pock, and Peter Schröder and Max Wadecki on this. And so here is a very brief overview. I would like first to show you some examples what this is all about and what one can do with a proper understanding of geometry in certain shape spaces. So then we will develop a geometric calculus, first continuous calculus, just reviewing this, and then discretizing this in a particular fashion in time. And then I will show applications of this time discretization for different shape spaces. We will discuss briefly the convergence properties of this discrete calculus, and then for a very specific, more advanced model, the metamorphosis model of images, we will discuss geodesics and results on Moscow convergence of certain time discretization. And finally, I would like briefly to talk about splines and not just geodesic paths in shape spaces. So here is some motivation. So we are in the space of images, and we have two images, like these images of bacteria, where there are red blood cells. These are the small darker ones, and one white blood cell, which is hunting little bacteria, which you see over there. This is at one stage, this is at another stage. And without knowing what is in between concerning the frames of the video sequence, we would like to reconstruct a proper motion. And that can be done by a computation of geodesic paths in the space of these viscous objects. Or let's consider this black object here, and then a slight variation of this. You can consider this theta as some displacement, a small displacement. And then with this as the starting variation, we can shoot a geodesic path. And you can not only do this, but you can also then extrapolate a texture on these objects to generate something which looks like a short running sequence. But it's not about objects. Images are frequently also characterized by really change of contrast, change of image color, but not only locally change of this, but transport plus change of intensities. And to treat this, we will study the so-called space of metamorphosis and the metamorphosis of images. And what you see here with these 9 images here, from here to there and to there, this is a geodesic path in the space of images with this model underlying. And here you see for 2 images, I think it's this one here and it's this one here, you see in black the motion field shown by small arrows. And what you in particular should see is that this velocity field changes in time. There is really a viscous flow underneath, which is part of this geodesic evolution. And what can you do with this once you have computed this, you can not only blend along a geodesic path, but you can, for instance, transport the texture from this object here over to this object. And that's what you see here. This is this head, but textured with this texture from here. So what else can you do? So you can do parallel transport. What is parallel transport? So you have a variation, an infinitesimal variation represented by a tangent vector of one object. So this is here the object in neutral phase, and the variation is a smile. And then you have another object here, which is a disgusted phase. You can compute first a geodesic path between the neutral phase and the disgusted phase. And then you can transport this variation from neutral to smile along this geodesic. And you end up here with a smile with a frown as the result of a parallel transport in a discretized fashion for sure. So what is the basic setup? We talk about manifolds with a certain Riemannian metric. Surely in most applications, these manifolds are infinite dimension. There is a length functional, and there is the path energy. So G denotes the metric, Y is my usual notation for foot points, and V is the velocity field here along this path. And then this is the general notion of path energy. And it's well known that minimizer of the path energy also minimize the length energy, with the advantage that they are of constant speed. And that is related to the basic Cauchy-Schwarz inequality, that the length can be estimated by the square root of the path energy. And this inequality is sharp for geodesic paths. And geodesics are local minimizers both of the length functional and the path energy. So here is now what is really the metric about in different shape spaces. So the toy model, which we keep in mind, is embedded Riemannian manifolds embedded in some Rm. And then we have embedded tangent vectors, and just taking the scalar product in the ambient space, we can define the metric. So then more advanced and interesting. So for instance, this parallel transport was of that type is the space of viscous shells. Shells are thin curved material layers of some thickness delta around the mid-surface S for shell. And this calligraphic S should denote the space of all shells. And now shells can undergo certain deformations. And there are two types of deformations which are in particular interesting. There are tangential motions, and there is normal bending. And there is theory known for that, at least separately. So it's clear that there is some gamma limit if we just look for the tangential distortion due to Ledouet and Raoul. There is for pure bending on isometric, in the isometric context, there is this classical result by Frieseke, James, Mora, Müller, that you can describe all this directly on the mid-surface with a rescaled energy functional W of the deformation phi. And so what has this to do with Riemannian geometry? So we can apply what is known as Rayleigh's paradigm and derive a model for viscous dissipation. So now the shells are no longer elastic, as it is usually assumed, but we suppose that the deformations we do are viscous deformations, raising to some dissipation. And there is viscous deformation due to tangential shearing or stretching and to normal bending. And we replace elastic strains from the classical shell theory by strain rates. And if we do so, then that's what you see here with the proper scaling, membrane energy, bending energy of first and third order in the thickness. The argument of the membrane energy is the Cauchy-Green strain tensor, and the argument of the bending energy is the relative shape operator, defined as representations in the metric of one of the two surfaces. And if you define this and then follow Rayleigh's paradigm, that means we consider the Hessian of this energy and interpret elastic strain and replace elastic strains by strain rates, then we obtain an object which is a good candidate for a Riemannian metric on the space of viscous shells. And indeed, it is true with this metric that the kernel are just those velocities which correspond to infinitesimal rigid body motions. Hence, defining the Hessian of this energy, the corresponding quadratic form as a metric up to this factor 1/2, is indeed a Riemannian metric on the space of viscous shells, modulo, which is fairly natural, infinitesimal rigid body motions. That's precisely what we would like to see. So what about viscous objects? That was this running sequence, for instance, in the application. So for here, we think of a certain object which is undergoing a deformation phi. This deformation is driven in time by an Eulerian velocity field VE. This Eulerian velocity field leads to the general viscous dissipation in Newtonian flows, which you see over here. The dissipation rate is defined as this here, where lambda and mu are the usual constants. And there is, in the sense of natures, a higher order term over here, with m being large enough to embed from the Sobolev space HM into C1 alpha. And epsilon of u is, as usual, the symmetrized strain rate. And now we can define a metric on variations of an object where we consider Eulerian velocity fields which keep the object constant and just perform the same normal variation on the boundary as generator of an equivalence class, and we minimize this viscous dissipation over this equivalence class. And that is a natural notion for a metric which measures the cost of a local variation of an object, which is here a viscous domain in space. And that is related fairly closely to the flow of diffeomorphism framework, which has been introduced in imaging already more than 20 years ago, where the object is just the whole space. But then, if you remember this image, these self-portraits of Van Gogh, there is more than just transport by some viscous flow field. The contrasts and the intensities can also change. How to take this into account? So we keep in the definition of the metric our dissipation term, dissipation of the velocity field. And then we consider a second term which measures the material derivative of the intensity map U. That means what happens in addition to transport along a motion path. And there is some penalty constant 1 over delta with a suitable delta value up front. And the material derivative for sure couples here the time and space derivative with the Eulerian velocity field. And therefore, we have in the definition of the metric here to minimize overall possible Eulerian velocity fields. That is for sure a very strong notion of a metric. And analytically, it's not a good idea to treat this as such. I will comment on that later. So this metamorphosis model has been introduced by Alain Trouvé and Laurent Jonas 16 years ago, and there are various contributions to this. So let me now talk about geometric calculus on Riemannian manifolds. So that's the standard thing. We go quickly over this. So there is, at first, that's the usual strategy. We first define a covariant derivative once we have a metric. And to define a covariant derivative, we need the Christoffel operator. And the Christoffel operator is nothing else but the representation of the variation of the metric. And once we have the covariant derivative, then we can solve this ODE and generate a parallel transport. If we consider second order covariant derivatives, we can ask for the defect of, let's say, Schwarz theorem on manifolds. This gives the definition of the curvature tensor. And so with the usual definition, I think the pattern should be sufficient for you to identify what we are talking about. And so that's one set of tools. Furthermore, there is the exponential map. This is if we solve this second ODE with this initial data, initial position, initial velocity, then this is what generates geodesic paths by solving ODEs, that is shooting of geodesics, and that gives rise to the exponential map. With an initial velocity v0 at position y0, at time 1, we end up at position y of 1. And the inverse of this is the logarithm. And with this technology at hand, we can now ask how to discretize this. And by discretization, I mean because we have seen many ODEs basically discretizing in time. Let me remind you, in the continuous setup, one starts usually with the covariant derivative. Then there is parallel transport, there are geodesics, there is the exponential map, there is the logarithm. This is how the theory develops. In the discrete context, it is completely different. You will see we will start with variation of geodesics. Then we will learn about how to compute the logarithm. Then the exponential map will appear as the inverse of the logarithm. With logarithm and exponential map in the discrete fashion, we can define discrete parallel transport. And with discrete parallel transport, we can finally come up with a definition of the covariant derivative. Yeah. So let's see how this works out. So first, in the continuous setup, let's consider here a curve from y0 to yk, and the y lowercase k's these are the time steps at time lowercase k times some time step tau, and the tau is just 1 over the uppercase k. And if we look for the squared Riemannian distance of two consecutive points along a path, we obtain this straightforward Cauchy-Schwarz inequality. Now that's nothing else but combining on all the intervals this immediate Cauchy-Schwarz inequality, which we'll see over here. And equality holds if the paths are already geodesic paths. And that means we can approximate the squared distance if we can approximate this by some functional w, which takes two positions y and y tilde up to a third order term here. Then we can build this discrete path energy here for a sequence of y k's, k from 0 to uppercase k. The k up front here is just 1 over the time step, and we sum over these functions here. And we call it discrete geodesic, the minimizer of this discrete path energy. So you can consider this as some spring type model. So if you have a manifold and you have a chain of springs, and you put these springs, or the intermediate, the joints of the springs, you fix them on the manifold, you fix the two endpoints, and then you relax all the springs with all the joints on the manifold, then you end up with a minimizer of this discrete energy. And so if you look for this discrete energy, then the question is, what are now the necessary conditions for a minimizer? What are the Lagrange equations? Let us consider the variation with respect to yk of this energy. Yk appears twice, once in this term here and once in this term. So that means the Lagrange equation, we once have to differentiate with respect to the second argument. This is the yk over here. And once with respect to the first argument, that's the yk over here. And we have this set of equations for all the intermediate positions along this discrete geodesic. And that is the problem which we have to minimize. So how to define now a discrete logarithm? Let us recall what the continuous logarithm is. This is the initial speed along a geodesic, which ends up at time 1 at this position y tilde. Then log of y tilde with respect to the position y is this initial speed v of 0. And if we multiply all of this now with 1 over k, then the response of this logarithm is just a tau scaled. Tau is 1 over k, tau scaled initial velocity. And that means the discrete logarithm candidate is just the vector in our space here from y0 to the first variationally computed geodesic, discrete geodesic point y1, up to the scaling with k. Yeah? K times this initial vector from y0 to y1, this is what we define as the log ky of y tilde. Now we compute a variational geodesic, and then we pick the first time step. What about the exponential map? This is for a exponential. This is for a short 3-point geodesic, the single Euler-Lagrange equation. And now, usually, if we want to find a connecting 3-point geodesic, then we would like to find just the y1 here, given y and y2. That would solve the variation problem. But now we do it the other way around. Now we suppose there is a y1 given and a y, and we ask for a solution y2 of this nonlinear equation. If we find this, then we already know that y1, y2 is a short 3-point discrete geodesic. And that's something we can iterate, and that's an ODE solver, which has the nice advantage that once we computed this iteration, we have already immediately solved the whole system of Lagrange equations of a variational geodesic. So if we know, and that's true for short geodesics, that they are unique, then we reproduce a variational geodesic by this shooting scheme. So discrete parallel transport, how to do this. So let us first consider how to do transport in R2. along a straight line. We can do this by construction of a parallelogram where we just ensure that the two diagonals meet at the center. And now we translate this to a discrete geodesic. We start with this displacement wk minus 1 by solving a variation problem from the end point to the next point along the line. We compute a 3-point discrete geodesic here. The midpoint is this yk minus 1c. And then we take this point and shoot a 3-point geodesic and get to this position here. And then we connect the two, and that's the discrete next step of our parallel transport. And if we rewrite the corresponding Euler-Lagrange equations, that is this little system of two Euler-Lagrange equations for the two incorporated small discrete geodesic problems. And we denote this by this boldface P. And also this can be iterated along a discrete path. Yeah, but now it's well known that the covariant derivative can be reproduced by a difference quotient using the parallel transport. And we have now a discrete parallel transport. We just use precisely this difference quotient idea to define a discrete covariant derivative. We can do it one-sided, that's basically a forward difference quotient, or we can do it symmetric with a central difference quotient, which will be of higher order. And then finally, we can define the discrete Riemannian curvature. This is done by iterating these discrete covariant derivatives. And the key point is here that for the inner differentiation, we have to choose a considerably smaller time step than for the outer one, which is given here by this, for the central one, by this beta exponent, which has to be larger or equal to 3/2. And so this will be a construction where we know that there is convergence of the discrete objects to the corresponding continuous objects if we let the time step size tend to 0. So what are now assumptions under which we can do analysis and numerical analysis? So first, what are the assumptions on the continuous model? Now we assume that there is a separable reflexive Banach space V, and this is compactly embedded into a Banach space Y. And M should be the closure of a convex open subset of M. So we are in the setup of Hilbert manifolds, or Banach manifolds, but here Hilbert because we will now introduce a scalar product. Furthermore, there is this metric where the foot point lies in this Y space, or is interpreted as a Y space object, and the velocities are in this V space. And obviously, because we have bilinearity in the two arguments of the V and in the velocity arguments, that is nice to be handled. That's just quadratic and positive definite for sure. So their convexity arguments can be applied, but the foot point will be strongly nonlinear. And therefore, to develop a theory, we need that there is some compactness involved. That is reflected by this space. And then the G has to be equivalent to the V scalar product, and it has to be has to have this particular continuity modulus here. And now we consider Riemannian manifold, which we denote by M, and the metric is G. What are the assumptions of the discrete model? So first, we need this approximation quality here, which we already motivated initially. And then we need this growth condition here, that this W functional is bounded from below by some increasing function gamma, where the argument is the distance. That will allow us to prove existence of discrete geodesics. And then we suppose for all the convergence proofs, except for the convergence of the Riemannian, the discrete Riemannian curvature, that the metric is C2 and the W is correspondingly C4. So what are now the W functions for the embedded, for the examples for manifolds? So in the toy model, where we have an ambient space, we just consider the distance in the ambient space of the 2 points. Yeah? That approximates, if we get closer and closer to Y, that approximates precisely the metric in the corresponding direction. And that's very easy to do. In the case of the discrete viscous shell, it's even easier, because as you might recall, we started with a elastic energy, and the metric was the Hessian of the elastic energy. Now we can do a finite element discretization of this elastic energy. That is what is written here. I will not go into the details. And we just, for a deformation being the mapping from Y to Y tilde, we define our metric as the quadratic part, or as the Hessian of this elastic energy previously been introduced. That's also fairly easy to compute, much easier than really approximating a Riemannian distance. And what you see here below is already an example of a geodesic path of 2 poses of this elephant. And here is another example. So given is this object here and that object. From neutral to smile, we can generate a discrete geodesic. We can continue with our shooting method to make the smile really a big laugh, or to make on the other side the neutral even more neutral. And what you see below here is, in gray, is for this model the accumulated stepwise dissipation due to tangential stretching and shearing, and in dark gray is the bending part. And you see that this stays almost constant. This is what is known, that the metric along geodesic paths, if they are minimizers of the path energy, is constant. And the color code up here is coding the tangential distortion density on the surfaces. So basically you see where there is significant distortion during this evolution. That's also something you've seen. I already explained this. And what is now a shape interpretation of the Riemannian curvature tensor? So with a Riemannian curvature tensor, we can compute sectional curvatures. So the question is, what sectional curvatures on a shape might be, what are the 2-dimensional subspaces for which we compute the sectional curvature, which might be of interest? So we've already learned that on these viscous shells, there is a natural Hessian, a natural operator, second order operator attached to that physical problem. So we can compute eigenmodes as natural modes of variation of these shapes of this elastic energy. And then we span 2-dimensional subspaces based on these eigenmodes. And what you see here is now for the first 8 eigenmodes, which are depicted over here with as vibration modes. We see a color code. Dark blue is low, yellow is large. A color code of the associated sectional curvature. And what does this show? This shows somehow the coupling of certain modes of variation. For instance, mode 1 and 2, they are closely intertwined. So there is really, basically, these are vibration modes of the two arms of this cactus. And that is, if you look for the values, a large elliptic, so positive sectional curvature. And if you compare mode 5 and mode 3, mode 5 basically is, or better, mode 4 and 1. 4 is basically a vibration along the trunk, and 1 is a vibration of the arms. And there is a low curvature value attached, which is basically reflecting the detachment of these modes of variation. So basically with these, what is called in other applications, a confusion matrix, we see the local structure of the shape space via computing sectional curvatures of a particular element in this space. So how to choose now in the space of viscous objects the functional W to set up the discrete approach. So I remind you, it was about viscous dissipation, which was defining our metric. And similar to the Rayleigh functional before, we now study as approximate functions for the square distance between an object O and an object O tilde, an elastic energy with the constraint that it matches the O object to the O tilde object. And the assumption on the elasticity energy density is that the Hessian of the energy density should be the rate of dissipation. If this is true, then we get this approximation quality that this W is a second order, is an approximation of the squared Riemannian distance up to a third order term. And here you see a viscous deforming arm, hand from two poses, and on certain intersection planes here, color-coded the rate of viscous dissipation leading to this geodesic. Or here, the geodesic from a Q to an A, continued by geodesic shooting beyond the A, and the color coding of the underlying viscous dissipation. What do we know about convergence of the discrete calculus? So first, the basic thing is there is gamma convergence of a suitable extension of these discrete paths. So we just connect two consecutive points on a discrete path with a continuous short geodesic. And this is how we define the extension of the discrete energy. And then it's quite straightforward to prove that in the L2Y topology, we have really gamma convergence. Beyond that, we can also prove path convergence in the Sobolev space W12. That's a classical basic finite element argument, because our geodesic is a one-dimensional nonlinear elliptic problem, which we can Galerkin discretize, and our method is a Galerkin discretization with suitable quadrature rules, and applying Strang's lemma type of arguments, one can show this W12 path convergence. Then there is convergence of the discrete logarithm. That's also a finite element estimate. The discrete logarithm is at one position a derivative of the solution of an elliptic problem. And in 1D, there are really finite element W1 infinity estimates. And that's a particular W1 infinity finite element estimate, which is basically nothing else but the discrete logarithm. Again, taking into account a bunch of quadrature errors. But that's the general strategy. And existence and convergence of the discrete exponential map, that's just in infinite dimensions ODE error estimates or for a nonlinear problem. An implicit ODE solution strategy. And the same with the parallel transport. Basically, I have shown you this child's ladder construction with a parallelogram. And you basically have to do a Taylor expansion of this construction to show then with classical ODE type arguments that you get convergence. And the discrete covariant derivative, that is a nonlinear way how to approximate certain derivatives by difference quotient type ideas. That's a classical, so to say, consistency argument with a bunch of Taylor expansion tricks. And a little bit more advanced for this discrete Riemann tensor. Now, where important is, as I already said, that the inner time step is much smaller than the outer one. So that's all what I would like to present concerning this, this general framework with a couple of applications. So what still is not covered by this is this metamorphosis model. And I would like now to talk about this. So the question is how to define our discrete W functional, an approximation of the squared Riemannian distance in the case of metamorphosis. We've already seen that this elastic energy pops up in this flow of diffeomorphism or in this viscous object case, including this higher order natures type term of multipolar fluids. So the question is how to discretize the covariant derivative. But that's very easy. So if there is a deformation and I compute the evolving function at the new time under this deformation and compare it to the old in a squared fashion, that is a difference quotient of the material derivative. And if you now look for the whole functional, that's something which is in imaging fairly well known. That is an elastic registration energy. So that means an elastic classical registration energy is nothing else but our approximation of the squared Riemannian distance. And if we sum up over this as before, then we obtain the discrete path energy. So what is now known for discrete geodesic paths? So we would like to talk about to get some Moscow convergence result. So that means at first we need to have the extension. That's slightly more tricky than before. But you can consider here on the image UK -1 straight line connections given by these deformation fields to positions in the image UK. And what you then do in space-time, you just interpolate intensity values here at this mouse position and the intensity here at that mouse position precisely along this straight line. For sufficiently large K, that's something you can always do. And that generates an interpolation operator in space-time given a sequence bold U of images and a sequence bold phi of deformations. And then, as usual, we define our continuous version of the discrete energy as precisely the discrete energy of, so this should be, sorry, this should not be a calligraphic E, this should just be there's a mismatch. This is the discrete energy. Sorry for this. Yeah, and infinity else if this is not an interpolated path. And then the result is that we get Moscow convergence of this discrete sequence of functionals. That means we have weak convergence considered in the lim-inf estimate and strong convergence in the lim-sup. That is what distinguishes Moscow convergence from gamma convergence. And as the usual consequence, because there is surely equicoerciveness, if you look closer to this, we know that minimizers of our sequence of discrete problems actually converge strongly in L2 in space-time to minimizers of the continuous path energy. And that leads to evolutions as such. And this Moscow convergence proof is also an existence proof of minimizers. Yeah? In particular, because we can generalize these models, and we can, I'm not talking about this today, we can consider images. There are, like in diffusion tensor imaging, many applications of this where the image map doesn't map into a Euclidean space, but maps into a manifold. So an image is pointwise mapping into a manifold. And then you can do also metamorphosis. And with this type of approach, you can also prove existence in this setup. So here you see what I already told you. So we have here UA, we have here UB. Now we take this geometry and this texture and combine them correspondingly. But there is one shortcoming, which I haven't told you so far. If you directly apply this for these portraits, then it doesn't work. It doesn't work with the clothing, and it doesn't work with the ear, and it also requires some recoloring of the background. That's what we've done so far. But you can replace classical RGB space by a much higher dimensional space, telling you about the structure of the image locally. And that is what comes with the deep convolutional neural networks, which you can use to classify images via feature maps from the image space into some, in this case, 64-dimensional space. That is a tool which is already heavily used in imaging. And you can now use this in this metamorphosis model as well. Instead of considering image maps as RGB maps, we consider image maps after some application of these fixed deep neural networks as maps into feature space. And then all these problems are gone, and you get very nice approximation sequences, even of fairly apart objects, like this cat here and this tiger over here. What you see here is the transition curve. The teeth are really nicely transported and deformed. The tongue, here. Here you see a certain a doubling of teeth for the RGB sequence. Sorry. That is so. And this problem is completely gone for the feature space sequence. So finally, let me take you 2 minutes to the spline business. So we are talking about a lot about geodesic curves. But if you think of, let's say, a shape like my body with 3 poses, one is like this, the other is like this, and the third is like this. So then if you do interpolation to animate this with piecewise geodesic, then it looks like this. I'm not a robot. So what we actually would like to see is a smooth interpolation of these keyframes. And that's what you see here with the cactus, these three poses. You can play this robot game, which is here colored in green, or you can smoothly interpolate, as I did it over here, really running through the keyframes, but in between smoothly interpolating. And that is here a piecewise geodesic, and here a spline in the toy model on the sphere, and here in this shape space of viscous shells. What is the spline energy? Now we know by de Boer that the classical spline energy is splines are minimizing the squared acceleration of the path. What is acceleration in the Riemannian manifold? Is the covariant derivative of the velocity. So that is the natural choice. And it's very important here not to stay with this energy, because then there is even not existence of spline paths. You have to add a positive constant mu times the path energy to get existence. And but then one can prove that there exist really interpolating splines under the conditions which we discussed initially, plus some slight additional condition. And one can, but maybe I'm here a little bit quicker, one can also discretize this with our W functional with the suitable scaling, where here this y tilde is linked to the neighboring points as being the midpoint, the geodesic midpoint, discrete geodesic midpoint of the two. And then one can build, summing up, a discrete spline energy, and one can prove also gamma convergence of the discrete spline energy to the continuous spline energy. And what you see here, this is this measure of the discrete acceleration, so to say. The green curve plots the acceleration along the piecewise geodesic path. Along the geodesics, there is no acceleration, but there are big peaks at the interpolation points. These are the kinks I'm doing over here. And they are completely smoothed out along the orange spline path here, in this case, of this facial animation. Sorry. And the final question this evening is, what has this to do with football? And here is just an outlook. What you can do with this is you can play the game of Riemannian PCA, principal component analysis. Given large sets of input data, you can compute first modes, which are then the PCA modes of this family of input data, like many human models. And you can use this to analyze certain motion patterns. So here are these principal modes on a huge database of human data shape capture. And here is now the approximation of a typical football sequence, where you see here the weights needed on these color-coded components to generate this football sequence. So let's look forward in 1 hour for the football game. And thanks for your attention.
Thank you very much.